Okay. Should we start? It's time. Okay. So there we go. Okay. It is my great privilege today to introduce the invited speaker for this session, Leslie Ann Goldberg, who is Professor of Computer Science at Oxford. Leslie's, I think I would say, made a number of fundamental contributions to the field of counting complexity over the last 3 decades. Ever since she obtained her PhD in '92 from Edinburgh, I believe, working with Mark Jerram and Alistair Sinclair. And then she's held positions at a number of places before moving to Oxford, including at Warwick, Liverpool, and I think before that at Sandia as well. She's very well known for her work on counting complexity and has been much recognized and awarded, including receiving the Suffrage Science Award, which I read about only recently. Without further ado, I will hand the floor to Leslie, who will tell us about approximately counting graph homomorphisms and retractions.
Okay, thank you.
Sorry,
Anit.
maybe before I do, could I just say, so if you do have a question during the course of just put it in the chat, and if it requires an interruption, I will interrupt Leslie. So just do that. Okay.
Okay, thanks. And please feel free to do that. Hopefully it'll work. Okay, so thank you very much for the invitation. And I'm sorry not to be in Goa, actually, but still glad to be joining the conference. So Nikolai told me that you'd be quite interested in hearing about work on approximately counting graph homomorphisms. So that's what I'm going to talk about. And I've decided to combine two different strands in the talk. So first, I'm going to tell you kind of about earlier work on approximately counting graph homomorphisms, which is kind of introducing the kind of foundations of approximate counting. What are the issues? And actually, I'll tell you about a surprising amount of things that we don't know, even though we've been doing it, as Anuj indicated, for a very long time. Then towards the end of the talk, I'm going to move toward restricted homomorphisms like list homomorphisms and retractions, and tell you about some more recent work along those lines. Okay, so let's start out by just reminding everybody or telling everybody what a homomorphism is. So a homomorphism from a graph G to a graph H. So here's a, oops, that doesn't work too well, does it? So stop it. Okay, here's G and here's H over here. You can see my cursor probably. And a homomorphism is just a function that maps the vertices of G to the vertices of H that matches edges to edges. So for example, this graph G, I could map V2 to blue. If this is H here with the red, blue, green, I could map V2 to blue, V3 to green, and this edge V2, V3 will go to blue, green. So edges go to edges, but I wouldn't be able, so this is a homomorphism, but I wouldn't be able to color V2 red because then I would have V1, V2 go to red, red, and that's not an edge of H. Okay, so that's a homomorphism. And what we're going to be interested in is counting homomorphisms. And I want to just say from the start that it's going to be useful to allow loops in H, such as what's shown there. And that's because loops help encode more interesting combinatorial structures, as I will show you. Sometimes we get stronger results by forbidding loops in G, and I'll just tell you about that as we go along. But I just want to introduce one bit of terminology. If we say that G is irreflexive, it means that it has no loops at all, like this graph here. And if we say it's reflexive, it means that every vertex has a loop. And of course, it doesn't have to be either of those. Okay, so that's just the definitions. And homomorphisms capture lots of interesting structures, as many of you probably already know. But in case you don't, I'd like to just kind of give a couple of canonical examples. So for example, if you let H be a little 2-vertex graph with no loop on one vertex and a loop on the other, like that, then homomorphisms from G correspond exactly to independent sets of G. And the way to see that is, what's a homomorphism? Well, I map all the vertices of G to blue or red, and I'm not allowed red, red. So red means in the independent set, and so homomorphisms are exactly the independent sets. And the other really classical example is I could take H to be a clique with no loops, so an irreflexive clique, maybe a 3 clique like that. And homomorphisms from G to H are now just proper colorings, because what can I do? I can take the vertices of G, I can color them red, blue, or green, but I don't have any loops over here. So I can't have any, I can't have a red, red edge or a blue, blue edge or a green, green edge. So it's a proper coloring. Okay, so at this point, what you should know is just what is a homomorphism. And if that wasn't clear, I strongly encourage you to interrupt, because the rest of the talk will be seriously boring if that wasn't clear. Yeah. Okay, so now what are the computational problems that you can ask about homomorphisms? Well, the first one goes back a very long time, almost as old as, well, as old as I've been doing this. So the graph homomorphism decision problem. So what's the problem? We fix a graph H, that's the target. The input's an irreflexive graph, no loops. And the question is there a homomorphism to the target? And there was this kind of really amazing result back in 1990 by Hell and Nesitrol. And what they showed is that if you fix H, then the complexity of this problem can be just completely classified. So they showed that the problem is in P if H has a loop, or if it's bipartite, but for any other H, it's an NP complete problem to answer this homomorphism problem. And the tractable cases are sort of very easy to understand. So if H has a loop, of course, there's a homomorphism to H, because you could just map all the vertices of G to that one vertex that has a loop, and that would be a homomorphism. If you had a bipartite graph H, then again, it would be really easy to see whether there was a homomorphism to H, because if your graph G has an odd cycle, there's nowhere for it to go. So the answer is no. But if it's bipartite, then you just have to decide, which vertices go to the bottom, which go to the top, and then you can, well, you could even just map them to an edge. That's the right way to say it. Okay, so that's very easy. And the amazing thing about the result, which I still think is impressive 30 years later, is that they showed for every single other H that there is, it's always hard. So that was a really lovely result. 10 years after that, Dyer and Greenhill, sorry, Catherine, looked at the counting problem. And what they showed is that they could get a similar dichotomy for counting. So let me start with a case where H is connected, because it's easier to explain. And the problem that they looked at is you take an irreflexive graph G, and you fixed H, and you want to output the number of homomorphisms from G to H. Okay, so what did they show? Well, if H is a clique with all loops present, it's easy to do that. Why? If I wanted to count homomorphisms to this H, well, the answer is 3 to the n, right? You can do whatever you like. Everything's a homomorphism. If you want to count homomorphisms to a bipartite graph, well, G had better be bipartite. Then this is what I started to get into last time. You just better decide which part of G goes to the bottom and to the top, and then you just sort of count them up. And again, they managed to show that everything else is number P complete. So that's, again, a complete classification and a lovely result. Okay, so that's the background for this problem. Oh, and I should just point out this little vertex here this is a degenerate complete bipartite graph for which the problem is easy. Okay. So I'm going to be interested in approximately counting homomorphisms, but before I can really tell you anything about that, I have to tell you a little bit about approximate counting, because it's, if you haven't seen it before, it's a little different from decision and exact counting. And so I just want to tell you a little bit about what are the relevant complexity classes and what sort of things can come up in approximate counting. Okay, so as you saw with decision, we have, as you know, essentially two things, or at least two relevant things here. Problems that are in P, problems that are NP complete. Then for the counting problem, we've seen FP, that's functions that can be computed in polynomial time. Number P, that's the, some people call that sharp P, that's, hard counting problems. Now let's look at approximate counting. And confusingly, there are actually three relevant complexity classes. So I'm just going to talk you a little bit through them, what sort of things come up most naturally in approximate counting. Just as in other parts of complexity theory, things can get as hard as you like, but I'm not going to make them as hard as you like. So I'm going to work within problems in number P, and homomorphism counting problems are going to be within that. Okay, so what approximate counting problems are there in number P? Well, the three really important classes. At the bottom, we have the problems that are really easy to approximate. So counting problems where approximation is easy. What does that mean? Well, certainly ones you could solve exactly are easy. Typically, the measure of easiness that we use is fully polynomial time approximation scheme, which just means that you can get within 1 plus minus epsilon of the answer, a factor of 1 plus or minus epsilon, but you're allowed time polynomial and 1 over epsilon. But honestly, it's very robust. And if you don't like that, just ignore it, because any definition you take will be the same for this course. So easy stuff is what you can do within a factor of a polynomial. It's what you can do within a factor of 2. It doesn't really make any difference. If you can do any of those things, you have an FPRAS. And if you don't, you don't. Okay, so examples there are counting satisfying assignments to a formula in disjunctive normal form, to coloring, that sort of thing. Okay, that's the easy stuff. Hard stuff. Hard stuff is things like counting satisfying assignments to a Boolean formula, counting the independent sets of a graph. And the thing I mainly want to say about that is these problems are actually not number P hard to approximate, but they are NP hard. And that's actually about as hard as you can get within approximate counting, because every problem in number P can be approximately counted with an NP oracle. So the hardest thing you can do with approximate counting is to be NP hard. And there's a bunch of equivalent problems that are. Okay, there's a third class of problems, and we usually call that by the name BIS, named after the kind of canonical problem in this complexity class. BIS is the problem of counting independent sets, not of a general graph, but of a bipartite one. So kind of a priori, it's not clear why this problem is so important, but again, it just turns out there are loads and loads and loads of complexity problems that are equivalent to BIS. So various partition functions in statistical physics, or counting stable matchings of a certain form, or counting downsets in a partial order. All of these problems are equivalent to BIS. And the general state of knowledge is that we know there's no FPRAS for these problems up here, unless NP equals RP. Of course, there is an FPRAS down here. And the middle ones, we believe that there's no FPRAS, but we also don't really believe that they're complete from number P under approximation preserving reduction. So there's genuinely three different classes here. And just like decision and exact counting, they're kind of Ladner-like theorems. So if these three classes are different, then there are infinite hierarchies around here. But the good news for us is that we're interested today in counting homomorphisms. And as far as the world knows, everything about approximating homomorphisms fits into these three classes. So we don't expect anything. Well, we don't know, but you'll see. But these are the relevant classes. Okay. So let's go back to a very old warm-up. So this goes back to 2003. And when we first knew about these classes, we started with a little warm-up, and we said, gosh, let's look at every connected 3-vertex graph H, and let's figure out how hard it is to approximately count homomorphisms to H. And this picture shows the result. And you can see two green graphs H here. which we already know counting homomorphism to these is easy exactly. These are Dyer and Greenhill's trivial graphs. And there's one graph here depicted in blue where it's actually bis equivalent to count homomorphisms to that graph. This graph actually has an interpretation. It's counting homomorphisms to this graph is actually the same as counting configurations in a statistical physics model called the Whittam-Rollinson model. But I'm not going to talk much about that. Everything else is equivalent to number sat, it's NP hard. So that was nice. And back in 2003, we thought this was very exciting, and we imagined quite soon that we would be able to classify all graphs and not just 3 vertex graphs. But here in 2021, I can announce to you that we've not completed this project. And even that there's a graph with 4 vertices that we don't understand. So if you want something to think about, if the talk is too slow for you, then I encourage you to consider this particular graph here, because we still don't know whether this particular graph, whether counting homomorphisms to this graph fits into one of these classes or where it lives. So we know that counting homomorphisms to this thing is bis hard, but we don't know whether it's sat hard or whether it's bis easy. Just as a little kind of fact about it, we do know that it's as hard as counting 4 colorings of a bipartite graph. And the way to see that is that if you look at every vertex here, they've each got 1 vertex they don't connect to. So maybe that gives you an idea that that's a little like 4 coloring, where there's 1 coloring that you can't get. But anyway, so this is already open. So you've already seen an open problem. We know other such problems. And to our shame, we don't even actually know how to classify irreflexive trees. So we're a long way from being done, but nevertheless, I'm going to spend the rest of the talk telling you things we do know and some more things we don't know. Okay, so one of the things that we do know is that there's actually nothing going on below bis in the homomorphism counting world. So let me just say what I mean by that. So remember, we have this picture there. So we have easy stuff, bis, hard stuff. And there's nothing below bis, because if you take, let's just start again with the connected H. If you had a connected H and it's not, just a complete bipartite graph or a fully looped clique, then actually counting homomorphisms is bis hard. So we don't know the complexity of everything, but we do know they're all bis hard. Okay, so I thought I'd give you a flavor of this result. I'm not going to give any proofs in this talk, but kind of interested in showing you why are they all bis hard? How can you see that? And it's a kind of inductive proof based on the kind of structure of the graph H. And actually it goes back to some earlier work with Kelk and Patterson on showing hardness for sampling homomorphisms to H. And that was all we could do for about 10 years. And then we came along and discovered that Lovász had given all the great ideas we needed back in 1967. We just hadn't noticed. And so some very nice work of Lovász helps you to put this together. Okay, so let me just give you a quick idea of the idea, just to show you what's going on with these homomorphisms. So suppose you have some graph H, and this is the graph I want to look at, and you wanted to show that counting homomorphisms to H was bis hard. So you wanted to use it to count independent sets of a bipartite graph, or equivalently to sample them. And I'm going to just use that equivalent because independent sets are self-reducible, so sampling and approximate counting are the same, and I'm just going to slide between them for that. All right, so here's H, and we want to show it's hard. So the way you might do that is you might pick out a neighborhood of some maximum degree vertex. Well, conveniently, I gave you an example where there's only one of those. So this vertex V1 has degree 4, everything else has smaller degree. And look at its neighborhood, a graph H1. Well, by induction, you probably already know that counting homomorphisms to H1 is bis hard, and indeed we do know that. So how do you proceed? Well, you could count independent sets in a bipartite graph if you could only count homomorphisms to H1. So if you had some graph in which you wanted to count independent sets, you could construct a graph where you just need to count homomorphisms to H1. That's G primed here in this picture. Then what you do is you connect G prime to some new vertex, which is connected to a ginormous independent set. And then let's imagine what happens if we look at homomorphisms from G to H. Well, because of this huge independent set, in a typical homomorphism from G to H, this vertex W will be a high degree vertex, because then you get a lot of entropy here, a lot of stuff going on, right? You got more choices. So in a typical homomorphism from G to H, W is going to be colored with V1. Well, that's lovely, because then you can look over here and what do you find? You find a homomorphism from G prime to H1 and you're done. So that's a flavor, but a super cheaty flavor, because I gave you a graph where there was a unique vertex of maximum degree and then totally built my argument on it. So before we leave this, topic, I just want to talk a little bit about what would you do if you didn't have a unique vertex of maximum degree. So let's look at this vertex H here. And here I've made life harder because every vertex has degree 4. So now there's two kinds of vertices. Like if you pick a V1 in the middle, I hope you can see it when I wiggle my cursor around. Yeah, okay, good. So if you pick V1 in the middle, then the neighborhood of V1 is this graph H1 here. But if you pick a corner vertex, the neighborhood looks like that. So there's two different graphs. And lo and behold, by induction, they're both bis hard, but now I want to show that this one is bis hard. So how do we do it? Well, in the sampling world, it's pretty easy, because we know that, and I will talk about sampling for a second. We know that if you could sample a homomorphism to H1, you could pick out an independent set in a bipartite graph. Similarly, you know that for H2. So suppose I have a bipartite graph and I want to sample an independent set. Well, what I do is I pull a graph G1, where I would only need a homomorphism to H1. I create a graph G2, where I would only need a homomorphism to H2. I glue the famous W in the middle, and I grab a homomorphism from G to H. Now, the excellent news is that W has to go somewhere. So if it goes to the middle vertex, then I know I should look over here and I'll find a homomorphism to that and I'll be done. But if instead W happens to have a corner vertex, then yay, I look over here and I find a homomorphism to H2 and I'm done. Don't know in advance which one will happen, but something good will happen and I'll recover my sample, count independent, then I can sample independent sets in a bipartite graph, hence count them. Okay, so that's the kind of idea. How do you change that to a counting problem? Well, what Lova showed was that if you take two graphs that are not isomorphic, H1 and H2, then there always exists some graph J, which has a different number of homomorphisms to H1 as to H2. And actually using the same technique, you can see that if you have a bunch of graphs that are pairwise non-isomorphic, then you can pick a graph J that'll pick out one of them. So there's an I star, some graph in there, and a graph J, such that the number of homomorphisms to HI star is bigger than any other. And what you do is you put that together with this kind of gluing idea, you stick some J gadgets around, and lo and behold, things work out. Okay, so that's all I want to say about vanilla homomorphisms. We know they're all bis hard. We don't know whether they're all bis easy. We don't even know about that if they've got a 4 vertex graph. And also, I swept under the carpet whether H was connected, and later in the talk that'll be legal, but here it was completely illegal because we don't know what to do if there are multiple components, or at least not in general. So for example, here's a little graph which actually has 2 components. This is independent set, so it's hard. This is trivial, so it's easy. But the graph H, which contains both, actually has an FPRAS. And the reason for that is essentially that 3 is bigger than 2. And so if you if you take a graph G and you want to count homomorphisms to this whole thing, then if you don't care much about the accuracy, you could just say 3 to the n. And if you care a lot about the accuracy, because epsilon is tiny, then you have enough time to do brute force and work out the answer. And that idea will go quite a long way, but we don't have a nice criterion for disconnected graphs. Okay, but what I want to do now is move on to restricted homomorphisms, not because this problem of homomorphisms is uninteresting. Indeed, I really hope that you or we or someone will finish the picture here for homomorphisms, because there's much we still don't know. But let's move on and look at some easier to deal with problems where we've made a bit more progress. And so I want to start by looking at the list homomorphism problem. So there's a lot of symbols here. You can probably ignore them because the picture is going to explain it better. But what is the list homomorphism problem? Well, we're still counting homomorphisms to a graph H. The input still has a graph G, but now in addition to being the graph, the vertices of G have lists which say where they're allowed to go in H. So the homomorphisms that we're interested in this particular instance, there's a list that says this vertex actually has to be colored red. And this list says, well, this vertex could be mapped to red or to green, but not to blue. This vertex has to be blue, and so on. And so the idea is that you want to count homomorphisms that satisfy all these list restrictions. Okay, so that's the list homomorphism problem. And let's go back to exact counting. And it's an easy extension of Dyer and Greenhill's result that the complexity of list homomorphism counting is exactly the same as without the lists. So why is that? Well, the hard cases were hard without lists, so they stay hard if you add lists. They could only just get harder. You don't have to use the lists. You could make them all the list of all vertices. So all you have to do is check that the easy cases are still easy with lists. And yeah, they are. So like if you look at a looped clique, and if I had a graph G and I had lists on every vertex, then every vertex could be anything in its list. And similarly, if I had a bipartite graph H and I had lists on all the vertices of G, well, I decide which side G will go to, upside or downside, and then I just multiply up what the lists allow. So quite easy, nothing to do. But for approximate counting, list homomorphisms turn out to be actually different in a kind of surprising, well, to me, way. And fortunately for us, this is something we do understand because we do actually have a full trichotomy for list homomorphisms. Okay, so this is a result joint with Galanis and Jerem. And what we showed is that if H is a connected graph, then the list homomorphism counting problem is either trivial, it's solvable in polynomial time, or it's NP hard, it's SAT equivalent, or it's BIS equivalent. And the BIS equivalent cases are from two particular classes of graphs, which I'm going to tell you about in a moment. So for the list homomorphism problem, we perfectly understand which ones are easy, which are in the middle, and which are hard. Okay, so I'm going to tell you about these exciting graph classes, but first I want to just make a few comments. Here, unlike before, the connectivity assumption is without loss of generality, because with lists you can zoom in on a component using the list. So the list homomorphism problem is as hard as its worst component. Also, I want to mention that this the theorem extends to the case where you put degree bounds on the graph G. And that's a very valid thing to do because applications in statistical physics, that's super important. So I'm not going to go into the applications, but they really do care about degree bounded graphs. So I'm just going to state the theorem in its more general form. So I'll use L-hom delta of H to be the list homomorphism counting problem when the input graph is degree at most delta. And with that notation, well, if it's trivial, then it's trivial for all delta. If it's hard, then it's hard for all delta at least 6. And if it's bis equivalent, then it's bis equivalent for all delta at least 6. So what that means, what does that mean? So that means if I look at the problem where G has to be restricted to have degree at most 6, then even for that restricted class, I get the same trichotomy as in general. So these two graph classes are bis equivalent, trivial ones are easy, and everything else is hard. Now, the actual degree at which the problem, you might say, well, what about delta smaller than 6? You know, there are other numbers besides 6, namely 3, 4, and 5. And if H happens to be reflexive, every loop is there, or irreflexive, no loops, and we're in the neither of these two cases, then we actually know sat hardness for degree 3. So that's everything you can possibly say. But there's some, you know, we don't understand for a given H in here, what happens if G has to be degree at most 3, 4, or 5. Now, 6 is optimal if you want the theorem to work for all H. And that's because, for example, counting independent sets in a graph of degree 6 or more is hard, but counting independent sets in a graph of degree at most 5 is something we can do approximately. So if you want a theorem that it goes for all H's, then 6 is all there is. On the other hand, for particular H's, there's room for refinement in here. So that's something quite interesting, like for fixed H's, what happens if you restrict a smaller degree? And the right threshold would therefore depend on H, and I'm not going to say any more about that, but there's interesting stuff to be done there. Okay, but instead of talking about that, what I'm going to do is I'm finally going to tell you what these fancy classes are. So which H's lead to bis equivalence instead of to easiness or hardness. So there are two classes of graphs that are bis equivalent. They both have long names. So irreflexive bipartite permutation graphs and reflexive proper interval graphs. They are hereditary graph classes, which means they're closed undertaking induced subgraphs. And they both have multiple characterizations. And I'm going to show you two of them. One characterization makes it okay to show bis easiness. The other characterization is okay for showing bis hardness, but they're the same class. So that's how we capture bis equivalence there. Okay, so first of all, let's talk about bis easiness. So there's two classes of graphs here, bipartite permutation graphs and proper interval graphs, depending on whether they're loops or not. But they both have a similar feel. And here's the kind of feel. So I've drawn you a picture of a 0-1 matrix here. And if the best thing is don't read the words, just look at the picture. This matrix is in staircase form. So I'm just going to tell you what that means, but the picture shows you what it means. The ones are all together in every row. And if you look at the beginning of the ones, they're increasing or at least non-decreasing, and same with the end. Okay, so that's a staircase matrix. And the two classes of graphs that lead to bis equivalent list homomorphism counting problems are exactly those where the adjacency matrix or the bi-adjacency matrix can be put into staircase form. So depending on whether irreflexive or reflexive, it's either the adjacency matrix or the bi-adjacency matrix that's in staircase form. That's what these graph classes are. And the staircase form helps us to show that counting homomorphisms is bis easy. So that's bis easiness. But how do we know that counting homomorphisms is bis hard, list homomorphisms? Well, the way that we do it is if H is not in these two classes, then I claim that everything is sat hard. Every list homomorphism problem is NP hard. And the way we do that is that both of these classes also have excluded subgraph characterizations. So let me just tell you about that. I'm not sure if I made that very clear. So I've got two graph classes, irreflexive bipartite permutation graphs and reflexive proper interval graphs. Graphs in these classes are the ones whose adjacency matrices can be written like this. That means homomorphism counting problems for them are easy. If you're not in these two classes, then that actually means that H has some particular induced subgraphs, and we're going to use those induced subgraphs to show actual hardness for counting list homomorphisms. And what I'm going to do is I'm going to focus just on this first class, irreflexive bipartite permutation graphs, but they're quite similar. Okay, so here's another definition. H is a bipartite permutation graph if and only if it has following subgraphs excluded as induced subgraphs. So it doesn't have an induced subgraph that looks like this, doesn't have an induced subgraph that looks like that, doesn't have an induced subgraph that looks like that, and furthermore, it doesn't have a cycle of length not 4 as an induced subgraph. Okay, so that's something that was well known in the graph classes world. And so going back to our picture, if it has the matrix form, yay, we get this easiness. Otherwise, we know we have one of these famous induced subgraphs. And all I'm going to do is show you briefly, why would an induced subgraph like this cause homomorphism counting to be hard? Okay. So we're not going to do a proof, but I'm just going to give you again a vibe, as in if you have an H that has an induced subgraph like this, why should it be hard to count list homomorphisms to H? And to show you that, I want to introduce really informally one of the most famous problems in approximate counting, which is the easing model. And I'm not going to do it in any kind of formal way. I just want to tell you about the easing model. So the easing model, the input is a graph. And what you do is you color the vertices of the graph, color 1 or 2. And along an edge of a graph, if you have an edge that has a 1 and a 2, so it's not monochromatic, then that contributes some big weight. But if you have a 1 and a 1 or a 2 and 2, that just contributes weight 1. You multiply the weights over all the edges, and the easing model partition function just says, can you add up the weights of all colorings? Okay, so the reason that counting list homomorphisms to a graph that includes this graph here that the structural graph theory people call X3 is that we can easily use X3 together with lists to mimic the easing model. So I'm going to show you how to do that, and that's for two reasons. One, that it's super canonical. The exact same thing works for every other induced subgraph you might care about. Two, it's going to trigger us to move on to retractions, because I'll show you what goes wrong. Okay, so let's just bear with me for a minute. It looks a little weird that I care so much about X3, but let's look at X3 and let's just think about it for a minute. So what I want to do, we could make the adjacency matrix of X3, but instead of writing down the whole adjacency matrix, I just want to zoom in on some little piece of it. So here's a little piece of the adjacency matrix, and it's the one involving vertices 1, 2, and 4, and 7. And I'll tell you why in a minute, but first let's just look at it. So what does this little piece of the adjacency matrix look like? Well, 1 is next to 4, but not 7, so 1, 0. 2 is next to 4 and 7. Okay, so I get this little submatrix. Now, what's the point of this submatrix? It's got 1, 0, and it's off the diagonal. So the determinant of this guy is 1. Okay, just remember that fact. Okay, now I want to magic up a gadget, but don't just look at the top half of this thing and we're going to do the idea. Let's imagine that I'm trying to build a path from X to Y that mimics an easing model edge. Well, along here, I'm going to use a list to pin to 1 and 2. I'm going to use a list to pin to 4 and 7. So I get something there with determinant 1. You don't know yet why I care with the determinant is 1, but I'm going to tell you in a minute. You're not going to do the calculation because it's kind of boring, but you could do the same calculation here. And I promise you the determinant would be 1 in the same way, and here and here. But determinants multiply. So along this path, we get determinant 1. And indeed, I've multiplied that matrix for you. You should just trust me on the arithmetic, that if you multiplied all those matrices along here, you'd find that if you put 1 here and 2 here, there would be 2 ways to fill in the middle. But if you put 1 and 1, there would be 3. 2 and 2, there would be 3. 2 and 1, there would be 5. Okay, little matrix here, doesn't matter what the numbers are, it has determinant 1. But I played a trick on you because I swapped the order. It's 1, 2, and 2, 1. So when I put them back in the order 1, 2, and 1, 2, I have a negative determinant. A negative determinant exactly means things prefer to be different and not the same. And now if you just take the path and copy it underneath to make it symmetric, you get a beautiful matrix, which exactly is an edge of the antiferromagnetic easing model. So if you put a 1 and a 1 here and here, there are 9 things to do, but a 1 and a 2, there are 10. Okay, so that's just to say, let me just pop a bunch of levels. So if you're not in one of these special graph classes, then you have several important induced subgraphs, but each of them makes it super easy to just build an edge of the antiferromagnetic easing model. So you're sad hard. Okay, so we've seen for homomorphisms, there's no complete trichotomy known. There was, maybe we conjecture that there is one, but we don't know what it is. For list homomorphisms, beautifully, we have a complete trichotomy. What about problems in between? Well, the most obvious problem in between is the graph retraction counting problem. Again, skip all those boring words. Let me tell you what a retraction is. A retraction from a graph G with lists to a graph H is a homomorphism. But now the rules of the game are that the lists are super simple. I'm allowed lists of size 1, like here, this one has to be red, this one has to be blue, this one has to be red. Or I'm allowed lists that just say, you know what, anything goes. So these are the only 2 possibilities, lists of size 1 and lists that are the whole vertex set of H. And the retraction problem, a homomorphism is a retraction if it's a homomorphism that satisfies those lists. The name retraction comes from the fact that what you could do is you can embed a little copy of H in G and then insist that H retract onto itself, and that would be the same thing. But it's going to be easier for us to just think about it as a list homomorphism where lists have size 1, or else they're unconstrained. They have size everything. Okay, so that's the retraction counting problem. Now, for exact counting, the complexity of counting retractions is the same as homomorphisms and list hom because it sits in between and they were the same. So there's nothing to learn if you're doing exact counting. But for approximate counting, the reason I showed you this hardness is because it needed lists of size 2. And I'd have struggled a lot more if I only had lists of size 1. But retractions only have lists of size 1. So if you want to understand the complexity of counting retractions to H, it's going to be a little different. And in more recent work with Jacob Fock and Stan Drzewny, the best that we can do so far is we have a trichotomy for square-free graphs, which means graphs without a force cycle. Now, I'm going to talk in a minute about what's the big deal about force cycles, because that sounds a bit stupid. But yeah, let me tell you first a little about this result. So it gives us a classification for trees, obviously, because trees don't have cycles. But the most striking thing that we found when we proved this theorem is that, weirdly, there's a whole bunch of stuff that turns out to be bis equivalent. And it's just kind of strange. And there's a lot of strange stuff that's bis easy. And this extends beyond the square-free case. And so I'm going to start by just giving you a little tour of which problems we know to be bis easy or not for retractions, because it's the truth. So there's nothing I can say about it except for that it's kind of weird. So here it is. So let me just going to walk you through some funny graphs. So the first feature is that cliques, or in the square-free case, therefore triangles, they play a role in determining whether a graph is bis easy or not. And the role is kind of complicated because triangles can make things hard, but they can also turn things that were hard into being bis easy. So the graph on the left is sat hard, but it turns out the graph on the right is bis easy. And it's not because I added another vertex that made it easy. If you would delete any of these edges, it would become sat hard again. So this triangle is what makes it bis easy. And to just make the example a little bit more batty, this is our friend, the sat hard graph, but things can be super complicated and still be bis easy. So this long weird thing turns out to be bis easy. And in fact, what happens is that you can see this long path. It has a long looped path and it has some cliques up here. And then there's kind of a balancing. The size of the cliques determine how many bristles you can have down here, and that makes it bis easy. Okay, so that's a bit weird. And I'm going to go into that in a little more detail in a second. But so I just want to pop a bigger picture and let's see for which graphs counting retractions to H turn out to be bis equivalent. And the first class is a nice one. So caterpillars. So counting classes. So if a caterpillar is trivial, obviously it's trivial to count retractions to it. But if it's not trivial, then it turns out to be exactly bis equivalent. So that's something we know. And here's the wacko class. The wacko class we call H bis. And H bis says if you take any looped path and you attach some bristles and you attach some cliques, then it's bis equivalent as long as you don't attach bristles to the endpoints. And also for every vertex, if you look at the size of this clique, here 2, and you subtract 1, so 1, and then you do the same thing here, 3 minus 1 is 2. That's how many bristles you're allowed. Sounds a bit crazy. Okay, but in any case, here's the theorem. The theorem says, for square-free graphs, if every component is trivial, then it's in FP. Otherwise, if every component is trivial, or in that wacko H bis, or an irreflexive caterpillar, then it's bis equivalent. Otherwise, it's sat equivalent. Okay, so for trees, this gives us a nice classification because H bis doesn't exist. It's just trivial, irreflexive caterpillar, or hard. But other guys, we get all these funny problems that turn out to be bis equivalent. I'd like to mention that bis equivalence extends to counting homomorphisms, of course, but it also extends to some other things like counting surjective homomorphisms. Okay, can just see a few. I want to leave time for questions, so I'm just going to do one more thing, and that is I'm going to show you some separations, because we've talked about homomorphisms, retractions, and list homomorphisms. So the last technical thing I want to do is just to indicate that actually we do expect these to all be different problems. And so I want to give you some evidence of some form for that. Okay, so this graph here, which is like this, which the structural graph there is called T2. It happens to be true that counting homomorphisms to T2 is equivalent to approximating the partition function of a 3-state Potts model, which is a huge open problem in approximate counting. But if you would go from homomorphisms up to retractions, this one just immediately becomes sat equivalent. Okay, that's not hugely strong evidence for a separation, but at least it's evidence that if there's no separation, then Potts partition function is hard. Ferro, which is not necessarily what we believe at the moment. So that would be kind of, so if these have no separation, then that would answer the Potts model in perhaps a surprising way. Between retractions and Listholm, there's even more convincing evidence, because this particular graph here, it's bis equivalent to count retractions, but SAT equivalent to count list homomorphisms. So if those were the same, then we would have solved the bis, which we hope to do, but it's been sitting around for 20 years without much resolution there. So that would be a great thing. Okay. Right. So then I want to stop. So here we are. So that was the theorem. So if the component, so for square free graphs, if every component is trivial, then it's an FP. Otherwise, for these several classes, it's bis equivalent. Otherwise, it's SAT equivalent. And I think I'd like to leave it there then and take some questions. Thanks.
Okay, thank you very much, Leslie. Let me give you a round of applause on behalf of everybody here.
Okay.
So I haven't seen any questions on the chat. If you have a question now, could you just raise your hand? I see a number of raised hands, so I will go down in order. Mikowa, you had your hand raised? No?
I was clapping.
Oh, I see, sorry. Okay. Okay, so if you have a question, raise your hand in using the raise hand feature. Mina, please unmute yourself and ask a question.
Do you have some kind of intuitive explanation for why this would be the canonical problem capturing this intermediate class?
Okay, yeah. So the thing about bis is that it's kind of a parity thing. And so, okay, let me say something about independent sets in bipartite graphs.
Yeah, exactly.
Okay, so think about bipartite graphs, and there's two spins. A vertex can be in or out, okay? And then those words don't mean anything, so you could turn them around. And so on the left-hand side of the graph, you could use in and out. And on the right-hand side of the graph, you could use out and in, or you could use in and out. And whether the two-spin problem encourages sameness or differentness on the two sides, you can flip between those if you're bipartite. I'm not sure, that may sound fuzzy, but it's okay. Let me just back up a minute. Ferromagnetic problems, where we encourage spins to be the same, are intuitively a lot easier than anti-ferromagnetic ones, where you encourage them to be different. But in a bipartite graph, there's actually no difference, because you can rename the spins. Independent set is intuitively anti-ferromagnetic. You're encouraging difference. I mean, it's not symmetric, but it's making spins want to be different. But in a bipartite graph, actually, that doesn't hold, because you could have renamed them. And so that's intuitively why bipartite is different. But then, okay, so that's one answer. The other answer is that we just keep seeing more and more and more and more problems that turn out to be bis complete. So to be honest, when we first saw it in 2003, well, it's like all of complexity theory, we build houses of cards. And I probably did not expect that in 2021, bis would still be there. But then over the years, we just got more and more and more bis complete problem. Like, for example, the ferromagnetic easing model, if you have fields that encourage opposite spins, that's bis complete. And all these partial order problems. And so there are just so many things that are bis complete that, yeah, it feels different. It feels different from SAT completeness, but.
Okay, thanks. Yeah.
Are there other questions? Okay. Well, let me ask a sort of rather broad question. So you had list homomorphisms and retractions. I mean, are there other natural things in the range between just counting homomorphisms and well, these two particular ways of, shall we say, making the problem harder?
Well, I think a really I was going to scroll back, but it's not letting. Oh, there we go. So yeah, so we have these problems: homomorphisms, retractions, and list homomorphisms. I think actually a super. Okay, there's two really interesting things that I didn't have time to talk about. Probably more than that, but two that I can think of this second. One is that I haven't really talked about G. So far, G is the input. G is just anything. And then I said, oh yeah, maybe we could make it bounded degree. And that's interesting. And that leads to lots of problems we don't understand. But of course, we know lots of graph classes. And, you know, G doesn't have to be bounded degree. It could be, you know, all sorts of graph classes, restrictions you could place on G. And then the complexity would again be wide open and not understood. The other thing is that the whole talk, we fixed H and then we said the input is G and you want to count homomorphisms from G to a fixed H. But sometimes people do it the other way around. Fixed G and the input is H and you want to do and again, that leads to very interesting and very hard in terms of intellectually hard problems that aren't fully understood.
Okay. Chandra had his hand up. Would you like to unmute yourself and ask a question?
So what do we expect the BIS complete problem? What is algorithmically do you expect it to be? I don't know. I mean, my understanding of whatever little of this F process is that either you have an F process, it's very hard. So, I mean, this is, I guess, first time I'm hearing about this BIS completeness.
Right. Okay. So I don't know how you'll find this answer, but I'm going to give it anyway. This is what I believe. So I believe that complexity theory. This has gone much more abstract than your question, but I'll get back to your question. But complexity theory, it's about expressibility, isn't it? So things are hard in complexity theory because we can express all sorts of stuff in them, and that's how we prove hardness, and that's the one way we know how to prove hardness. But lots of stuff is hard while still being probably, well, not being so expressive. There are other reasons you can imagine for computational hardness that aren't maybe captured by expressiveness, right? So I think about, for example, Les Valiant's class number P1, where the input is n, and you want to count all Hamiltonian graphs with n vertices. The input is only n. So you're not going to encode satisfiability in it because you've only got n. But I don't think that's going to be algorithmically easy. Okay, that was maybe irrelevant, but somehow popped into my head, and it's something I kind of am interested in, like what else could we use to prove hardness? But now let me get back to the question with BIS and SAT. It wouldn't bother me personally if they were both different in terms of expressibility, but there are no fast algorithms for either. So that's where I'd put my money. I don't think there's an FPRAS for BIS, but it could still be less expressive than SAT. That would be my guess.
Okay. We had a question in the chat from Narayan Kumar Krishnan. Would you like to unmute yourself and ask a question? Or would you like me to read it out? Okay. I'll read it out. The question says, what about quantitative versions of this problem? For instance, put weights on the vertices of H and ask for a min-cost homomorphism from G to H.
Oh, great. Okay, that's another thing I should have said and didn't, so thank you so much for the question. So in fact, I didn't do it in this talk, but normally we do have weights. And in fact, all the statistical physics questions, I mean, they're not really interested in counting independent sets. They're interested in counting independent sets where there's a weight, lambda, for every vertex that's in the set. And then it's not just finding a min-cost homomorphism, but you could, for example, want to count weighted homomorphisms or to sample a homomorphism with probability proportional to its weight. All those are super interesting problems. We have some results about them. Sometimes we know BIS equivalence. Sometimes we know, sorry, I had an alarm. I'll turn that off. That was so I didn't go over. Okay. Sometimes we have this equivalence, sometimes we have sat hardness, but I'm afraid that we're a long way from having a complete classification with the weights.
Okay. Thank you very much. If there are no further questions, let me give Leslie another round of applause for that wonderful talk. And that's the end of this session. Thank you.
Thanks very much. Maybe next time we will be in Goa.
All right. Bye.
Bhaskar?
Yeah, Anu.